live from New York. No, we are in Laguna Woods, and it's the Laguna Woods Show with your host and moderator, Esther Grossfield. Here's Esther.
Hi, welcome to the Laguna Woods Show, where every guest matters. Today, we have a very special guest. He is a medical physicist, and his name is Dr. Thomas Kampp. Hi.
Hello.
Hi, Doctor.
Hello.
So nice to have you here.
It's a pleasure to be here.
So you are a medical physicist. What does that mean?
The essential responsibilities of a qualified medical physicist is to provide the clinical practice to assure safe and effective delivery of radiation to achieve diagnostic and therapeutic results as prescribed for patient care.
Huh. And you give a lot of speeches. What kind of speeches do you give?
Not too many, but I have been an invited speaker in Europe, United States, China. I've spoken about design considerations for mission-critical computer systems, the effects of radiation therapy on the cardiovascular system.
Yeah.
I was once a co-chair of a Congress in Washington, D.C. Gave the keynote address, which is trying to determine from symptoms what the underlying causes would be. Those are a few of the things I've done.
And you were teaching other doctors too, didn't you? You were teaching.
My last several years of practice was as faculty at USC Keck School of Medicine, Norris Cancer Center. I taught physicians in the physics of radiation therapy. I also taught a session in the radiation biology series. It was basically the presentation I gave in China, the effects of radiation therapy on the cardiovascular system.
So I was really surprised when you told me that a banana, you can tell that it has radiation. I mean, with the potassium. What is this all about?
Radioactivity is natural.
Yeah.
It is what it is.
Yes.
The definition of dose is very simple in concept, but if you're not trained in thinking this way, it's difficult. For example, if you take aspirin, 81 milligrams in an average body, 70 kilograms, 154 pounds, so you have so much dose per mass. Same with radiation, so much energy absorbed per kilogram.
Yeah.
But how many people actually understand what a joule is, a unit of energy? So what has come about is something that is quite approximate, but it's something that most people can understand. This is a banana. A banana contains potassium, and potassium has many isotopes. Isotope just means same place on the periodic table. That's all it means. There's a potassium-40, which decays and gives off radiation. That energy is absorbed. And so the approximate unit of dose would be called banana equivalent dose. I have some figures here, I think, to give some idea of what this means.
Yeah.
The average background in Los Angeles, for example, average daily background would be equivalent to 100 banana equivalents. Okay? Flight from London to New York would be 400.
What if a flight from London to New York would be 400?
Banana equivalent dose.
Huh.
So it's equivalent to eating 400 bananas. You don't want to eat 400 bananas at once. I mean, you'd go off the scale. Living in a stone, brick, or concrete building for 1 year is 700 bananas, banana equivalent dose.
So that means the house has radiation?
Of course.
Every house has radiation?
Living in a stone, brick, or concrete building. If you live in a wood hut, you don't get it.
Oh.
Because radioactive material is normal. It's part of nature.
Yes, yes.
All right?
Yes.
And so if you build things out of stone and brick,
Yeah.
they contain radioactive isotopes. They give off radiation. Now, dental x-ray. Oh my goodness. What do you get with a dental x-ray?
Yeah.
50. 50. You go from London to New York, that's 400. You live in Los
You
Angeles?
mean being on a plane, there is radiation on a plane?
Of course.
Huh.
Why?
I don't know.
There are sources of radiation from the ground,
Yeah.
from things you eat,
Yeah.
internal radiation.
Yes.
Cosmic rays,
Yeah.
all right? Radon that you breathe in.
Yeah.
You go up high, so you are above most of the shielding that the atmosphere provides, and so you get a higher dose from cosmic rays.
Ah. Yeah. I wanted to ask you, you were saying that there's a difference between fire and sun. Let's say when you're near a fireplace,
Yes.
you don't get like a burn, like you get burned being in the sun. What is this?
This is an excellent question. You ask good questions. Sunlight is natural, right? Everything is natural is good for you, is the common thinking, but it's not really thinking at all. One needs to look at things as they actually are. If you have a good book, you go outside for 10 minutes to read the book, and you're outside for an hour, what happens? Your skin burns, and then it peels.
Yes.
What are we talking about? If you go to the store and get grapes, they can come in packets. You get big packets, small packets, medium-sized packets. The same with light. Light, particles, packages of energy. Packet in Latin is quantum. Now you know everything about quantum physics. Energy comes in little packets. Okay. So the higher the frequency of the electromagnetic radiation, light, X-rays, gamma rays, microwaves, visible light, radio waves, it's all the same stuff. The only thing that differs is the frequency of the radiation, and this tells you how much energy per quantum, per packet. So ultraviolet light is part of sunlight. The energy per packet of ultraviolet light, ultra just means above, it's Greek, so you have your rainbow, I'll talk about that in a minute.
Yes,
so it's above your blues in the visible spectrum, and it contains enough energy, more energy than the binding energy of molecules. So it's absorbed and the molecules break up. It's a bit like billiards, boom, okay. But this changes the molecules. There is a gene called a p53 gene that if the cell is not working right, it will have programmed cell death called apoptosis, and the cell will die. That's how it's supposed to work. So then your sunburn peels. What's peeling are all these dead cells that were killed by normal, natural ultraviolet light. Okay. So now we have the rainbow, visible light. Our eyes are not falling out because they're all peeling and dying. So you know that with visible light, the energy is not strong enough to break chemical bonds, and so we can see without any problem. So the rainbow, if you think of a fictitious man, Roy G. Biv, you have the rainbow. Red, orange, yellow, green, blue, indigo, violet. Violet is the high energy end, red is low energy end, and what is below red? Infrared. That means below red in the spectrum. So when you warm yourself on a nice winter's day coming in from the snow and you have your cup of coffee or cocoa and you're in front of the fire and getting warm, the infrared does not have enough energy to break chemical bonds, so you just get warm and your skin doesn't get affected.
You told me that the rainbow, the red, has the least
Energy.
radiation.
No, it's all radiation, but the energy
Oh, it's less.
is less. Energy per quantum, energy per packet of energy is less. But it's not enough to break chemical bonds, but the energy is absorbed and warms you nicely without causing any problems. And then below that,
Yeah.
you have microwaves, non-ionizing, so it doesn't cause any problems. And below that are radio waves.
Do we as human beings have radiation?
Yes.
How?
We have radiation if you, all right, if you sleep next to somebody, that's worth half a banana. Because we not only have potassium, there are other elements that are normally radioactive. You have
Yeah.
carbon, for example.
Yeah.
Carbon-12 is a normal, stable. Carbon, there's also carbon-14, which is radioactive, and that's perfectly normal. The mammalian cells have repair mechanisms. They can generally repair sublethal damage. And these mechanisms are known to exist. How do we know? The 2015 Nobel Prize in Chemistry was awarded to 3 brilliant scientists who were investigating the mechanism of cell repair in mammalian cells. And so if there's some small damage, that can generally be repaired.
You know, you were telling me one time that they made a study about rats, and the rats that had the radiation lived longer than rats that didn't have radiation.
Yes, there was a partial study that was revealed,
Yeah.
caused a lot of furor in the press and people got all excited.
Yeah.
It's interesting because one, it was only a partial report. Two, it was not peer reviewed.
Yeah.
Three, if you look at the dose response, the effect did not increase with dose in all cases. Which meant that the correlation was very, very weak. Mm-hmm. If one does not have good statistics, there is something known as a false positive.
Yeah.
Nothing's 100%. You run an experiment, you may get maybe false positive, false negative. If you get a result that happens to be because of chance, that would be a false positive. So there's indications that these results were basically false positives. Don't believe me, trust but verify, do your own research. But what's interesting is the rats were radiated with radiation in utero while they were still in the mother's womb.
Oh.
We don't use cell phones in the womb.
Uh-huh.
You know. Also, microwaves are non-ionizing.
Mm-hmm.
They broke up the experiment into several batches. One was 1.5 watts per kilogram. That's called SAR, specific absorption rate. 1.5 watts, 3 watts, and 6 watts. And they exposed them 10 hours a day, 10 minutes on, 10 minutes off. All right. But there were some results that appeared to be statistically significant. The males who were irradiated with the radio waves lived, if I remember correctly, about 8% longer than the controls. And the females' data was not so strong, but they certainly did not live any shorter because of the microwave radiation. Okay, remember these numbers. 1.6 watts per kilogram, 3 and 6 watts per kilogram. So we have a smartphone. These are federally regulated.
Yeah.
One can go to Title 47, Code of Federal Regulations, Section 2.1093D2, which defines the maximum allowable power from these things.
Uh-huh.
Well, they define it in terms of SAR, as I said, specific absorption rate. Whole body SAR values not to exceed 0.08 watts per kilogram. That's 0.08 of a watt, okay? Specific dose cannot exceed 1.6 watts per kilogram. What's specific? That would be any 1 gram of tissue whose volume is in the shape of a cube. So you can get 1.6 watts to only 1 gram, that's maximum. But whole body is only 0.08 watts. The power levels are really quite low. There is no indication that there are no strong statistical correlations for cell phone use and, say, brain cancer that gets everybody excited.
But where can they read it?
That would be Title 47, Code of Federal Regulations, Section 2.1093D2.
They can read it there.
They can read it there.
That's the guideline, or what? What's that?
These are legal guidelines that cannot be exceeded by manufacturers of personal devices.
Uh-huh.
And if one considers Apple alone sold 1 billion
Yes.
smartphones.
Yes.
Okay. Other companies sold many smartphones as well. So one could ask, okay, what is the increase of brain cancer with all these phones out there?
Yeah.
There is no increase in the rate of brain cancer.
Huh.
So there's no evidence that really should make one worry. If I were worried, I would not use a smartphone, and I do. Does that
Yes,
help?
yes, yes, yes. You know, you would like to talk about global warming, and the thing is, we watched the opening of the Olympics,
Yes.
and they were talking about global warming. I was like surprised. I mean, not surprised, but they were talking about it, and they were showing pictures.
This is not a new problem.
Yeah, when did they start getting aware of global warming?
That would go back to 1896.
Yeah.
The brilliant chemist Svante Arrhenius, who got the 1903 Nobel Prize in Chemistry, made calculations based on measured data. It's not magical thinking. Based on measured data to estimate how carbon dioxide could increase the surface temperature by the greenhouse effect. The greenhouse effect basically is quite simple. If you go to a plant nursery, they have greenhouses. How do they work? Sun comes in, warms up the inside of the plants and the soil and things, but the infrared light cannot go back out through the glass, so it gets trapped, and so the greenhouse gets warm even if it's cool outside. So the sun shines on the earth. All right. Interacts with the ground and the trees and animals and Bambi and everybody else and gets warm. Then there are gases in the atmosphere that absorb this energy and retain it.
Yeah.
What do I have? I had the gases that are involved in absorbing the heat would be carbon dioxide, methane, nitrous oxide, water vapor. So the energy that's absorbed is retained by these and some other gases. If we increase the concentration of carbon dioxide and methane and other gases, the air warms up because more heat is retained and does not escape back out into space. And so you have this dynamic equilibrium. Well, some people say the sun is getting warmer and that's why it is. Well, actually, direct measurements of the sun from 1978 and indirect measurements of the sun show that the sun is actually decreasing in irradiance.
Really? Wow,
So
I wonder
it's
why.
not causing global warming if it's not getting any brighter.
Huh? It's decreasing, huh?
Slightly, but it's not increasing. And there's a difference between global warming and climate change. And this comes from the website www.epa.gov/climate-change/basics. This is, Environmental Protection Agency. So what is global warming? Global warming refers to the recent and ongoing rise in global average temperature near the Earth's surface. It is caused mostly by increasing concentrations of greenhouse gases in the atmosphere. Global warming is causing climate patterns to change. However, global warming itself represents only one aspect of climate change. So we have to differentiate between global warming and climate change. Okay, so what's climate change?
Yeah.
Climate change refers to any significant change in the measures of climate lasting for a significant period of time. In other words, climate change includes major changes in temperature, precipitation, or wind patterns, among other effects that occur over several decades or longer. So, greenhouse gases. As I mentioned, carbon dioxide, methane, nitrous oxide, and water vapor primarily. Carbon dioxide is now at 404.5 parts per million.
Now, and how,
Now.
how much were they before?
These levels have not been seen for at least the last 800,000 years.
800,000 years.
They've not been this high for the last 800,000 years. So, what are the consequences of climate change thus far?
Okay.
Oceans. Oceans are warming.
Yeah.
Carbon dioxide is absorbed and makes the water acidic. The acidity of surface ocean waters has increased by about 30% since the beginning of the Industrial Revolution, around the 1880s. Okay. The oceans absorb about 90% of heat trapped by greenhouse gases. Phytoplankton, these small little organisms, which form the basis of the world's marine food chain. These things are eaten by other critters that are eaten by other critters that are eaten finally by swordfish and so on. All right. If you don't have food at the bottom, you're not going to support the animals at the top. All right. And so they are influenced by change in acidity and temperature. They don't do as well. But they're also the source of more than half of Earth's oxygen.
What?
The phytoplankton in the ocean.
Wow.
Then also,
That's what we need, oxygen.
if the water becomes acidic, different animals that form shells out of calcium carbonate cannot form shells because calcium carbonate does not form in an acidic environment. So you want to eat your linguine now while it's still there. Sea level rise.
Yeah.
Global sea level rose about 17 centimeters, that's 6.7 inches, in the last century. The rate in the last decade, however, is nearly double that of the last century. And what does this mean long term? A 2-meter rise in the ocean levels will completely inundate New Orleans, and a 4-meter rise will completely inundate Miami and southern Florida. Global temperature rise. The Earth has warmed since 1880 by about 1.4 degrees. Most of the warming occurred in the 1970s. All 10 of the warmest years occurred during the past 12 years. Record number of high temperatures is increasing, and the record numbers of low temperatures is decreasing. So you have a trend that's increasing. As I said, even though the 2000s witnessed a solar output decline resulting in an unusually deep solar minimum in the period 2007 to 2009, surface temperatures continue to increase. You also have shrinking ice sheets and decreased snow cover. People say that, Antarctica is increasing in ice. It's not. The Greenland and Antarctic ice sheets have decreased in mass. Glaciers are retreating almost everywhere, including the Alps, the Himalayas, the Rockies, Alaska, and Africa. Land ice is decreasing by 281 gigatons per year. That's 281 billion tons per year. Arctic ice minimum is decreasing by 13.4% per decade. Antarctic mass variation since 2002 is decreasing by 134 billion metric tons every year.
So what can we do to save what is there
I tend to be a realist.
Yeah.
And so I try not to believe in magical thinking.
Yeah.
So where does one get information?
Yes.
I will reference some websites where one can get actual hard data.
You think knowledge is the key?
Knowledge is the key. You're absolutely right. Brilliant. So what I suggest, climate.nasa.gov, then www.noaa.gov, that would be NOAA, and that stands for National Oceanic and Atmospheric Administration. Then www.ipcc.ch, that's in Switzerland, that's why it's .ch, and that stands for the Intergovernmental Panel on Climate Change. What the Intergovernmental Panel does is to aggregate information from researchers all over the world and creates reports on what the global situation appears to be based on measured data. And then the final one would be www.3, number 3, www.epa.gov/climate-change/basics. And that's the United States Environmental Protection Agency. And then once one is educated and has a reasonable understanding, then let their education and knowledge guide them for the best behavior.
That's very good that people should know, and maybe everybody's going to start thinking about it, and maybe it's going to make some kind of an impact.
We need to work, humans generally, globally, need to work together to
Yes.
recognize, and the problem will only be solved by everyone working together in a positive way.
In a positive way. So you have another speech coming? Are you going to go for, do you have anything?
I've been invited to give a presentation.
A presentation.
In October. The date has not been set.
What
but
about?
It'll be in October, and it's about radiation in general.
Radiation, that's what you are specializing in. Okay. So, okay, so it was so nice having you here. It's already, time is
This is
went by.
really an exciting and wonderful time. Thank you.
you. So, thank you for watching, and next time we're going to have another interesting person. Thank you. Bye.